All right, so we shall begin. So I want to talk about modular arithmetic. All right, so let's give a definition. All right, here it is. Let A and B be integers. All right, we say A is congruent to B mod n, and write A equals B mod n if A and B have same remainder when divided by n. So, immediate theorem, A is congruent to B mod n if and only if n divides B minus A. All right? I'm going to foolishly look away from my notes for a second, see if we can prove it. I may regret that. However, I'm hopped up on watermelon at the moment, so I have a certain amount of energy. We'll see if it's enough. I don't know. It's debatable. Clearly, I don't like this definition. Like, I actually prefer what's in the theorem as a definition, right? Like A is congruent to B if they differ by a multiple of n, right? I mean, this is really if and only if what? B minus A is equal to n times k for some k in the integers while we're at it, right? That's really what that means. B minus A is a multiple of n. Or, even better yet, actually, honestly, here's what I think of it. B is equal to A plus nk, right? For some k and z. I mean, truth be told, that's how I think about it. B and A are congruent if you can get from one to the other by adding some multiple of n. That's really my intuition for equivalence, congruence, mod n. But anyway, let me try to play nice here with this remainder statement. So let's go with the forward implication, right? So suppose A is congruent to B mod n, right? So divide A by n, divide B by n, right? And obtain what? By the division algorithm, we get what? A is equal to, like, let's say Q1n plus R, right? And B is equal to Q2n plus R, right? And the same remainder. Why? Because we're assuming that they're congruent mod n, so they have the same remainder, right? So if we have that, then what's thus what? B minus A is equal to what? B minus A is equal to Q2n plus R minus Q1n plus R. The R's be canceling, and you get Q2 minus Q1 times n, right? Which does what? That proves n divides B minus A, right? Conversely, suppose, B minus, well, n divides B minus A, right? Then b minus a is equal to nk for some k in the integers, right? Let's just put that down there. Now what do we do? Well, we're going to divide a and b both by n. And then we're going to want to find an argument that proves that they have the same remainder, right? Okay, so use division algorithm to find a is equal to q1n plus r1 and b is equal to q2n plus r2. Where what do we get about r1 and 2? Where 0 is less than or equal to r1 and r2, which is less than n, right? We do have that. The remainders are at most n. For the sake of everything, like good and decent in the world, we assume n is a positive integer. If I ever don't say it, it's understood. And oftentimes it cannot be 1. For things like, I don't know, like mod 1. I don't know about mod 1. I guess you could do it, but it seems kind of dumb. All right, so I think mod 1 is just like basically everything is that one point. All right, anyway, what you got here then? We should probably look at b minus a, right? Because that's what we have information about. B minus a is equal to nk, but b minus a also connects our handy-dandy division algorithms we got here. So let's see what happens. B minus a is q2n plus r2 minus q1n plus r1, right? And so that's equal to q2 minus q1 times n, right? Plus r2 minus r1. But that's also equal to what? It's also equal to n times k for that, whatever k that is, right? All right, so, well, they're equal. So this gives me q2 minus q1 minus k times n is equal to r1 minus r2. So certainly we can take the absolute value of both sides of this, right? Agree? Yeah. So we got this guy is equal to that guy. Let me draw you a picture. So here's my picture. 0, n. But I should really include a circle there. See, because R1 and R2, they have to fit somewhere up in here, right? And what is the absolute value of R2 minus R1? I taught this in Math 100. Yeah, I taught this in my intermediate algebra class. Indeed, the distance between R1 and R2. And can the distance between R1 and R2, what's the most it can be? And not included. So this is less than n, right? But notice here we have the product of n and an integer.
Yeah.
So the only way that that's possible is, yeah, if this is equal to 0. Because otherwise you'd have q2 minus q1 minus k is something non-zero, and the product of that times n would be something non-zero, and it would also have to be larger than n, which of course is absurd because r1 minus r2 has to be less than n. So this implies r1 is equal to r2, which of course completes the proof because that shows that a is congruent to b. Right? All right. Now this is convenient. It's good to have gone through this because there are times where it is super nice to just be able to rattle off, oh, a and b are congruent because they have the same remainder. All right, so we've now proved that. Properties of congruence. Number uno, x is congruent to x mod n. 2, x congruent to y implies y congruent to x mod n. Actually, if you don't mind, I'm going to stop writing mod n everywhere because I'm already getting tired of it. So let us understand that equals 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 is mod n, yeah? So our custom in here is you can write at the top of a paragraph, this calculation is done mod n, and then, well, anyway, more about notation as we go on here, but x congruent to y implies y congruent to x. And property 3, x congruent to y and y congruent to z implies x congruent to z, right? And this is for all x, y, and z in the integers, right? So collectively, this gives me the corollary that congruence mod n provides equivalence relation on the integers, right? Because it's what? Reflexive?
Transitive.
Mm-hmm.
And symmetric.
Right, reflexive. This one is symmetric. And yeah, the last here is transitive. So let's prove, like, I guess we can prove those. Shouldn't take long. 1, if x is an element of z, then x minus x is equal to 0, right? Which is equal to n times 1, excuse me, n times 0, which is an integer, right? So therefore, x minus n divides x minus x, which implies that x is congruent to x, right? By my theorem. If the n divides the difference, they're congruent. So there's reflexive. 2, if x is congruent to y, then what? Y minus x is equal to n times k, right, for some integer k. But what's that tell us? X minus y is n times minus k, right? And minus k is an integer. So therefore what? X is, excuse me, y is congruent to x. Three. So if we have x congruent to y and y congruent to z, then that means that, let's say it this way. Okay, so y minus x is equal to n times k1, and z minus y is equal to n times k2, right? For some k1 and k2. What's that? Right, so consider, what was it? I'm trying to show x is congruent to z. I should look at z minus x, right? Yeah. So z minus x is equal to z minus y plus y minus x, right? And z minus y, which is equal to nk2 plus nk1, which is n times k2 plus k1. Now, if I was smarter, I think these are the same arguments we just went through for divisibility like 2 classes ago. So if I had my thinking hat on, we could just shortcut these and just use divisibility arguments, I think. But anyway, so there it is. Thus, x is congruent to z. All right. So if we have a relation on a set which satisfies these 3 properties, reflexive, symmetric, and transitive, it is an equivalence relation. And what does that mean? What are the rights and privileges guaranteed thereunto if you have an equivalence relation on a set? What does it do to the set? Remember, it partitions the set. Yeah. So equivalence relations partition sets. It partitions the set on which the equivalence is defined. And it partitions the set into disjoint equivalence classes, right? So what's the equivalence class? What is an equivalence class? So here it is, the notation I'll use for the starting point here, bracket x like that. So what you're looking at here is y in the integers such that y is congruent to x mod n. Now, so deficiency of this notation, of course, is that this notation has no explicit reference to the n, which is forming the modulus, you know? So that's kind of a downfall of this notation, right? But in a particular context, it's okay. Let's see here. Of course, you could also notice that this is what? This is x plus nk, right? Such that k is an integer. So if you know, the thing I erased a second ago, Other characterizations of congruence, well, one, you can get from one to the other by adding a multiple of n. So that's another way we could look at this equivalence. So this is the equivalence class represented by X. All right. Now, so, the first sort of most obvious example that's been with us since, the beginning of elementary school practically was even and odd integers, right? So look at that. The equivalence to like mod 2, right? If we take the equivalence class of, say, 0, it's equal to what? It's equal to 0 plus 2 times k, such that k is an integer, right? In other words, like explicitly, you just listing them out, 0 plus or minus 2 plus or minus 4 and so forth, right? In other words, the even integers are the equivalence class of 0 mod 2. And of course, the representative is not unique, right? No. You could just as well say that this is equal to like 2. Same animal. And so the equivalence class with representative 1 is what? It's things like 1 plus 2k, right? And so that, of course, is plus or minus 1, plus or minus 3, plus or minus 5, and so forth, right? Yep. Odd integers. And of course, you could pick different representatives like minus 71. Whatever. Let's get weird. Right? Now these, notice that the union, so here, the union of these, right, is the whole integers, right? Every integer is either even or odd. And what else can you say? So the union of the sets forming the partition gives the whole thing. And also the intersection of these is the empty set, right? So a partition is a collection of disjoint sets whose union covers the whole of the set. Ah, good. So another example, mod 4, right? You got yourself 0, 1, 2, and 3, right? So basically you're looking at 4k, 4k plus 1, 4k plus 2, 4k plus 3. Again, the union of these 4 disjoint equivalence classes gives you the whole of the integers. There it is. Now, I should mention, there is also something called coset notation, right? So I'll even introduce it in this example. The coset notation for this is something like 4z. So you could either write 4z plus 1, or you could write 1 plus 4z. I mean, it kind of depends on how you want to go. But with understanding, I'm trying to remember what I did in my notes that I wrote here. Seems like I've gone with 4z first. So I think it depends on whether you want to work with left or right cosets, as they're called in group theory. But anyway, this is what I've written here, so whatever. As sets, it's definitely the case that this is equal to 2 plus 4z, right? So I mean, it's kind of a question of style, whether you want to write it.
Yeah, we've already said it's symmetric.
one way or the other. But certainly the notation is just this. NZ is just multiples of n, integer multiples of n, right? And if we take any set plus any set of integers plus k, it's just s plus k such that s is an s, right? This is what we mean. This is how we define set plus a number. It's defined to be the set formed by element-wise addition of that number to the set. And this is the kind of knowledge that could get some undergraduates out of trouble when they write something fuzzy that doesn't have meaning. Because there's other classes where we're like, say, no, you can't add a number to a set. It's like, until you define it. So anyway, there we go. Now, of course, the Coset notation has the advantage of what? So if I come back up to here, right, I can do what? In terms of the Coset notation, this is just equal to what? This is equal to nz, right, plus x. And this Coset, the Coset notation has the advantage of manifestly indicating the modulus, right? You can see it. It's in your face. N. It's mod n. It's there, right? Hooray! And yeah. Now, so all right. So what's another notation? Another competing notation for this is like bracket x sub n. So if I'm doing calculations where I'm working in two different moduli, and I need to be careful because, you know, like 3 is not equal to, say, 3 9, right? Like 3 mod 3, this is 0. Because I can, you know, divide by 3, the same remainder is 0. And that is not 0 mod 9. So these are different things, and yet, of course, if you just write 3 not equal to 3, then you're like, no, bad notation, right? So like, reference the moduli when it matters. Yeah, that's all I'm saying. Not saying anything terribly deep there. Okay, so here we go. Proposition 4.11. Erase all this. Oh, I think I erased all this. So I should erase. Prop 4.11. It says if the equivalence class of x is equal to the equivalence class of y. Well, excuse me, not if. Note. The equivalence of class of x is equal to the equivalence class of y if and only if y. If and only if x is congruent to y mod n. All right. That's okay. That's the proposition. Oh, okay. It's fine. I just was misreading the thing after the proposition. Okay, so if we had a proper introduction to proofs class, this would have already been like covered there. If I was teaching introduction to proofs, I would cover equivalence classes and partitions there, and always refer back to it, because this is just a statement about equivalence classes, really. So, I mean, here it is. If you have x is equal to y, what's that mean? That means that the equivalence class of x is a subset of the equivalence class of y, right? But X is an element of the equivalence class of X since X is congruent to X, right? Thus, X is an element of the equivalence class with representative Y, because X, the equivalence class of X, is assumed to be a subset of the equivalence class of Y. Therefore, what? X is equivalent to Y, excuse me, congruent to Y mod n. So there's the forward implication of that.
I can see why you put in proofs.
Yeah, this has nothing to do with the structure of congruence. It has everything to do with the definition of equivalence class. This direction, if X is congruent to Y, right, then X is an element of the equivalence class. X is an element of the equivalence class of Y, right? All right. So let's see here. Let Z be an element of the equivalence class of X. Thus, X is congruent to Z, right? So we have X is congruent to Z. I should say it this way. I flip that around. Z is congruent to X, right? It's symmetric, so we know we can write it one way or the other anyway, but so Z is congruent to X, right? And X is congruent to Y, we're assuming that, right? Therefore, Z is congruent to Y, right? By transitivity, hence, Z is an element of the equivalence class of Y, because it's equivalent to Y. So what did I just do? I picked an arbitrary element in the equivalence class containing X, and I showed that it's an element of the equivalence class containing Y. That proves that the equivalence class represented by X is a subset of the equivalence class represented by Y. And by symmetry of argument, right? You can see that Y is likewise a subset of X. Yeah. Therefore, this is equal to that. Okay. All right. So what does this matter? Well, my immediate comment after this is this allows us certain calculations, right? Thus calculate, right? For example, 2 plus 8z plus, oh, I can't do it yet. Sorry. Dang it. Now you'll expect it. Curses. Showing my cards too soon. So like, 3 plus 4z is equal to like 7 plus 4z, right? You can add multiples of 4 and not change the representative, right? Because, or like mod 11, you've got like 20 is equal to 9 is equal to minus 2, etc. So you can add or subtract copies of your modulus and not change the equivalence class, right? All right. So we're just drilling down into sort of equality, if you will, in the world of modular arithmetic. Next up. Proposition 4.12. Here we go. If x is equal to x prime and y is equal to y prime mod n, right? Now, those aren't mod n, right? But I'm saying that these are equivalence classes with respect to the congruence mod n, right? And they're equal. They have different x and x prime, y and y prime. These are congruent mod n, right? So they give the same equivalence classes. Then here we go, numero uno. The equivalence class of x plus y is equal to the equivalence class of x prime plus y prime. 2, the equivalence class of xy is equal to the equivalence class of x prime y prime. 3, the equivalence class of x minus y is the equivalence class of x prime minus y prime. My corollary to this just restates the same in the other notation, right? Like this says x plus y plus nz is equal to x prime plus y prime plus nz, right? And xy plus nz is equal to x prime y prime plus nz, and x minus y plus nz is equal to x prime minus y prime plus nz, all right? That's the corollary. What's the proof? So I'm basically just going to make use of the previous proposition. And I'm going to exploit. So, okay, first of all, x equal to x prime implies x prime is equal to x plus nk1, right? And y equal to y prime implies that y prime is equal to y plus nk2, right? For some k1 and k2 in the integers, right? Let me check my battery. I think we're okay. Yeah. All right, so let's do it. Number 1, x prime plus y prime, what is it? It's equal to x plus nk1 plus y plus nk2, right? But that's equal to x plus y plus n times k1 plus k2, right?
K1 plus K2 is some K.
Right, yeah, you can definitely see that x plus y is congruent to x plus y plus n times k1 plus k2, right? That's true. Therefore, this is equal to x plus y by the previous proposition. That's 1. 2, we've got x prime y prime. That's x plus nk1 times y plus nk2. Multiply it out. xy plus n times, well, k1y plus k2x plus k1, k2. But clearly, xy plus is congruent, right? Mod n to x plus y, or excuse me, xy plus n times, I'm tired of writing this. I'm going to call it my happy face. Happy face. Wait a minute, that's not a happy face. That's a Pac-Man. Come on. All right, there we go. So anyway, again, by proposition 4.11, here we go. Oh, sorry. Don't matter. And I will just say the proof of 3 is similar, all right? I don't enjoy writing down there. What does this mean? What do these mean?
These propositions.
I mean, what is the significance of these here?
Equivalence classes can be have what's it called? Have direct mappings, such that you can add multiply and subtract.
Here, let me make a definition. I think you're on the ball. I think you got the right idea. Let me just kind of steer you a little bit into some words. Definition. Modular arithmetic. All right. Let n be a natural number. And define x plus y is equal to x plus y, and x times y is equal to xy. So here I'm defining the addition of equivalence classes and the multiplication of equivalence classes by the corresponding addition of representatives or multiplication of representatives. And of course, although if you want, you could throw in minus here too, right? Now, in the other notation, this looks like what? X plus nz, right? Plus y plus nz is x plus y plus nz. Definition, right? Now the thing you have to worry about here is whenever you make a definition that's based on a representative of an equivalence class, the question is it well defined? Is it a function actually? See, because if we got different, if the right-hand side, depending on which representative, let me get rid of the minus, it's just tacky. If we took, if taking different representatives, x prime and y prime, gave us a different x plus y prime over here that wasn't equal to x plus y, representative equivalence class from that, then it wouldn't be single valued, right? We'd get a different outcome for different representatives. And so that's, in other words, proposition 4.12 shows that these definitions are well defined. So that's all I'm getting at. Shows addition and multiplication are well defined for the equivalence classes, right? Now,
It's a lot better way than I
Yeah, it is indeed they do define nice. Now, okay, so furthermore, definition. So that we've been using words, but I never actually came out and told you the notation for the set of equivalence classes, right? And so the notation is as follows: z mod n z. This is equal to the set of equivalence classes. Mod n. So modular arithmetic is defining a arithmetic operation on the z mod n z, right? And now this, we also abbreviate this, of course, as just z sub n, right? That's another notation for this, right? And so that's how we can add and multiply in modular arithmetic. All right. What are the properties? What are the properties of modular arithmetic? So, lots of nice properties, right? Lots of nice properties. Okay, so I'm getting very tired of writing. I'm going to, at this point, I'm going to bail on the current cumbersome notation and introduce yet another one. Okay, so let's let the equivalence class containing x just be denoted by x with a bar over it. That's like a lot easier to write.
I'm not going to get mad at the comments with it.
I mean, we started with set builder curly bracket notation, right? Then we introduced this bracket notation. I played a little bit with the coset notation, right? Now I've replaced it with a bar over it. Before it's done, we'll just write x. But anyway, so x bar plus y bar is equal to y bar plus x bar. xy bar is y bar x bar. X bar times y bar plus z bar, x bar y bar plus x bar z bar. And you have the other way as well, x bar plus y bar, z bar is x bar z bar. I mean, it's silly. I've always found it silly to write down both distributive rules after you've said that the multiplication is commutative, but everybody's doing it. So, I'm just a victim of peer pressure. What can I tell you? And so commutative addition, commutative multiplication, distributive rules, and we also have associativity of both addition and multiplication. I guess I should add some parentheses, huh? So you could go with this, or you could go with that. You could go with this, or you could go with that. Associativity. Oh, and there's an additive inverse. Additive identity, right? Like x bar plus 0 bar is x bar, right? And x bar times 1 bar is x bar. So there's an additive identity, there's a multiplicative identity, right? Furthermore, we can define exponents, right? Like, and I'm gonna write it up here because I don't like to write down here, but sorry. So like x, let me just show you here. X times x, right, is xx, right, which is x squared. So of course, this is what we would think of as being x squared. So you see how that works?
Yeah.
And you can use induction to kind of see that this just as well goes for x to the power k is equal to the, like that. But be careful, that has to be the same k. You can't like reduce the exponent mod n. That's not one of the places. There's lots of places where you can reduce things mod, like multiples of subtract off multiples of n. But these exponents, all right, it's more complicated what happens there. All right, so those are your, and of course these likewise extend to like finite numbers of sums and products inductively, right? All right. So modular arithmetic. Now, so what? So suppose a child comes up to you and says 2 plus 2 equals 12.
We're not doing this.
We're not doing this? No, you can use modular arithmetic to make nonsensical arithmetic statements of children make sense. Mod some whatever, you know. And modular arithmetic, honestly, it's pretty old. Like modular arithmetic is already in the water as soon as you start thinking about like a cyclical definition of time.
I've always thought, like, I mean, you know how, like, the reason we're in base 10 normally is because we have 10 fingers?
Right.
You know, I've thought of modular arithmetic since then. You know, like, since counting started.
I agree, yeah.
Have a basis of,
I think that's definitely on point. And like there's so much of what I'm doing in trigonometry right now is really modular kind of arithmetic, the idea of coterminal angles, you know, multiples of 2 pi or multiples of 360. So let's talk about the decimal representation of a number for a second, like base 10, right? So if you have n as an integer and it's base 10 representation, what's it look like? So if you say like n is equal to, let's say, ak minus 1, a1 and a0, where that's like the base 10 representation. I'm trying to remember. Well, here's a possible notation for base 10 representation, all right? Like, usually we wouldn't write that. We'd just write what? We would usually just write ak minus 1, ak, right? ak minus 1, a1, a0, right? Like that's just our decimal number. And we traditionally put commas for every 3 or something. But what does that actually mean? That actually means, well, let's see here, ak times 10 to the what? Plus ak minus 1 times 10 to the what? Plus plus a1 times 10 to the what? Plus a0 times 10 to the what? All right, so let me just be less abstract here for a second so that you guys are on board with me. 352. Usual base 10 representation. This is,
3 100s,
right, 3 100s,
5 10s,
5 10s.
2
So you can see that this is supposed to be a 0, this is supposed to be a 1, this is a k minus 1, and this is a k, right? So this is the decimal representation of an integer. You can write it as a sum of powers of 10. So let's think about this. What if we want to look at mod 10? Right, mod 10. What's this? Mod 10, so we've got ak times 10 to the k, right?
Yeah.
a1 times 10, right? Plus a0. All of this is a multiple of 10.
Yep.
So this is just equal to a0.
Yeah.
So what is the remainder of any integer divided by 10? Right. Just the ones. This proves that. Right? Going back to what we started with today. What's the remainder of n divided by 9?
N divided by 9.
If I take n divided by 9, what's the remainder?
N divided by 9.
What is remainder? And I shouldn't be using n here. Let me not use n. N's the wrong letter. N is exactly the wrong. N is so entirely the wrong letter here. Oh man, I'm an idiot. Let's call it anything but n.
Okay.
Anything but n would be wonderful. Like, how about x? Because n, I want to think of as the modulus, you know? All right. This 10 is my n, right? In the way we've been using it. My bad. So that's probably half the reason you're confused, right? I just changed notation midstream. I was once accused of my notation in linear algebra meaning nothing. I took it as high praise. No. It's not a...
X divided.
What is the remainder of x divided by 9?
Would be all the numbers left over.
Mm.
Aren't not divisible by 9.
Well, we know that
I'm just using straight up division algorithm.
it's x, right?
Yeah.
And so like we can reduce x mod 9, right?
For a while.
And so the question is how to do that. Well, notice this. Mod 9, 10 is what? 1 plus 9, right? Which is 1, right? So 10 to the k is 10 to the k is 1 to the k mod 9. It's just 1. You see, so when we look at the equivalence class containing x mod 9, we look at the decimal expansion. If we have the decimal expansion of x, it's just the equivalence class of the sum of the digits. And that is the remainder. That's why a number is divisible by 9 if and only if the sum of the digits is a multiple of 9. Something we're all taught as children. 81 is a multiple of 9 because 8 plus 1 is 9. 54 is a multiple of 9 because 5 plus 4 is 9. You know?
Yeah.
How about 375?
I knew that for 3. I did not know that for 9.
Is that divisible by 9?
No, it's divisible by 3 though.
Let's see here. So 10, 15. This is congruent to 15 mod 9, right? Which is congruent to 6.
See, that doesn't work with all numbers though.
Oh, no, it does not, right. What about if you did division by...
4 is the best.
It actually gets somewhat complicated for some other numbers. Like 11 is kind of nice. I mean, 10 is the stupidest of all, right? But mod 11, like how about divide by 11?
12 is nice.
Mm-hmm.
We use base 12 a lot.
What would be the remainder by divide by 11? If we're doing mod 11, how's it go? Well, 10